Okay, this is 8.2. We're looking at types of chemical reactions. And really there's 5 types here. There's synthesis, decomposition, single replacement, double replacement, just like I've written down here. Not quite that easy though. So what we'll end up wanting to do with this information is we'll want to be able to identify what type of chemical reaction, but really we are doing that so that we are able to write chemical reactions and predict what the products would be in chemical reactions. And part of the way to be able to predict how something is going to be able to react is to see, what types of reactions are there and what possibilities do we have. So our first one is synthesis, and these are just images from your book. In the synthesis reaction, and notice this is also sometimes called a composition reaction, so we have to be careful because different types of reactions, depending on what text we look at or what standards we look at, can have different terms. So this isn't universal, calling things synthesis reactions. It's very common. It's in the Minnesota standards. It's in our book. So that's what we're going to use as a synthesis reaction. If you think of synthesis is a hard word for me to say, obviously. But what it means is we have two things coming together to make one thing. Typically, we have a reaction like this. Kind of our classic example that we looked at in class is this one, magnesium and oxygen, O2. Magnesium and oxygen come together. We make magnesium oxide. I'm going to balance that equation. This is a synthesis reaction. We have two elements coming together to make one. Now, metals like magnesium often react with oxygen to make oxides. That's a very common reaction. So other times that we see metals, say like iron, we can predict that it will react with oxygen to make an oxide. Now, this is the difficulty with iron, is depending upon the circumstances, we can make two different oxides, and probably will make a little of both in most reactions. But most metals are going to react with oxygen to make an oxide. That is a classic synthesis reaction. So if we ever see a metal, we see oxygen, we can think, probably going to make an oxide. We can put those things together. Okay, another type of common synthesis reaction is having an alkali or an alkali earth metal reacting with a halogen. Now, these are forming our classic ionic compounds that we've looked at before. So here we have halogens with alkali metals. Here we have halogens with alkali earth metals. So if we see that type of scenario, we know it's going to form an ionic bond, and we can predict what that product is going to be. So we have synthesis reactions so far. We look at metals with oxygen to make oxides. Also, alkali earth metals reacting with halogens. And we don't have to memorize all of them. I just want to give you different examples that fall under these categories. We need to know the top 5, and the more types of reactions under those that we know, the better we'll be at this. Decomposition simply means we take something and we break it apart into smaller pieces. So synthesis is putting stuff together. Decomposition is breaking it apart. Often our decomposition reactions involve heat. So notice in all of these examples they're giving you in the book, there's a little triangle. That means we're heating these things up to decompose them. A classic example of a decomposition. I think decomposition reactions actually are the hardest ones to predict what the products will be unless we've seen a lot of decomposition reactions. And that's why I'm showing you a lot here from your book, and not all of them, but kind of some classic examples. If we have a carbonate, a CO3, if we heat up that carbonate, often we'll get CO2 out of it. And then whatever's left over. So notice this is calcium carbonate. And notice this is a balanced equation. It actually forces out CO2 and leaves behind what's left, calcium and oxygen. So that's a classic decomposition. So if we heat something, we see bubbles of gas, probably decomposition. Decomposition of metal hydroxides. Now this one, again, probably not going to really know what it's going to produce unless we've seen this pattern before. If we have a hydroxide, and metal hydroxides are common compounds, heat that up, we drive out the water, and again, leave what's left over. So this one, we're driving out the water, what's left over, calcium oxide. Notice we're using calcium in these examples, but you could replace that with magnesium carbonate and magnesium hydroxide. It would do the same thing. Or you could put in potassium carbonate, potassium hydroxide. We'd see a similar pattern. So that's what we're really looking for, is we're looking for patterns. Another classic one is a chlorate ion. So the ClO3, if we heat it up, we drive off the oxygen and leave behind an ionic substance. That was actually a little bit dangerous, because any time you're heating something and giving up oxygen, wow, you make the environment really kind of able to spontaneously combust things, because we have lots of oxygen. Really able So dangerous lab, actually. Don't do it in a chemistry lab anymore. It used to be a classic chemistry lab, I think, until multiple high school students got burned. Not here, by any means. And somewhere else, maybe. Okay, single replacement. So we have synthesis. We have decomposition. Single replacement, I think, are a little bit easier to see. Typically, kind of like this says here, we're going to see replacement of a metal by another metal in a compound, and that's going to be actually our next unit, is looking at when a metal will replace another metal. So in the single replacement reaction, one element comes in and it replaces the other, kicks that one out. Notice A kicks out B here, bonds with X. B now is all by itself. We can also have the second element be replaced. It doesn't always need to just be the metal. So looking at a few of these, notice in this one, aluminum and lead nitrate. In this one, aluminum comes in, kicks out the lead. Lead's all by itself. Aluminum is now bonded to the nitrate. So that is a single replacement reaction. That is one metal replacing another metal. The metal replaces it because this metal, aluminum, is more reactive. So notice what it says here. Aluminum is more active than the lead. So we have a whole reactivity series of metals that's going to predict whether or not these things are going to react. Because now on this side, notice there's only an arrow going in one direction. This will not go back the other way. So if you have a solution of aluminum nitrate to start with, and you throw in, lead, that would give you no reaction. And that's important to know when we don't have chemical reactions too, because lead is more reactive, so it won't let go of that bond to the nitrate. Lead cannot replace it. So we do have metals that will replace other metals. We just need to know our activity series. Not a big deal. We'll figure that out here in the next section. We can also have that metal replace hydrogen. We can look at where hydrogen is on the reactivity scale, and that sodium will come in, replace a hydrogen, kick it out as hydrogen gas, and bond to that hydroxide. So in this scenario, what I want you to see when you look at water, and what we'll think about a lot of times now when we look at water, is don't think about it as water. Don't think about it as covalently bonded dihydrogen monoxide. Let's think about it as hydrogen hydroxide, HOH. And that's how it's reacting in this instance. This is still a single replacement. Sodium is coming in, replacing that hydrogen, kicking it off, and bonding to the hydroxide that's left over. So that's how it's a single replacement reaction. Single replacement will also happen when we have metals with acids. So metals can replace other metals if they're more reactive. They can replace hydrogen in water. Again, they have to be pretty active to do that. A lot of them will react also with metals and kick out the hydrogen out of the acid and bond to whatever salt is in that acid. Notice, like we said, we can also see this in the second position, in the halogens. So chlorine can come in and replace bromine. Fluorine can come in and replace chlorine, forming that bond, kicking out chlorine. Notice there is a reactivity series for these. So as we go up the periodic table of our halogens, remember fluorine is the most reactive, followed by chlorine, followed by bromine. So the more reactive nonmetal will replace the less reactive nonmetal. So that's why, notice chlorine, which is here, can replace bromine, which is below it on the periodic table. But notice bromine cannot replace chlorine. So bromine is less reactive, so it cannot come in and replace chlorine. So say we put bromine with potassium fluoride, well, again, we're going to have no reaction. No reaction. And why? Because, again, bromine is further down the reactivity. It's not as reactive as fluorine. It cannot rip that fluorine off and bond to the potassium. Okay, so once again, synthesis reactions, we have two things coming together, like metals with oxides. We have decomposition reactions, and there's a lot of examples of that. Again, I think it's kind of difficult. That's one I need to spend a lot of time looking at myself sometimes. Single replacement, often a metal replacing another metal, or a halogen replacing another halogen. Now double replacement reactions. In double replacement reactions, they really switch spots. So we have, in this generic example, you have AX and BY, and A and B really just swap spots. So A is bonded to Y, B is bonded to X. Okay, when we see this type of reaction is often when we see precipitate reactions. We have two aqueous salts. In this case, one aqueous salt is lead nitrate. Aqueous, again, means it's dissolved in water. We're mixing that lead nitrate with potassium iodide. But now when they make an insoluble solid, the precipitate lead iodide. So notice we have potassium iodide. Here we have lead nitrate. Now we have a double replacement. The potassium bonds to the nitrate, the lead to the iodide, and then boom, we have an insoluble solid and also an aqueous ionic salt left over. This is an example of double replacement. Again, most of our double replacements are going to be exactly like this. They're going to be formations of precipitates. And again, that's something in a chapter further down the road, we will be able to look at those metals and predict what is going to be the salt that's going to be formed. We can also see some double replacements like this where we form a gas. Not going to see that as much, but we will see examples like this where we have formation of water. Now this often, like I said, sometimes these are given different names. This is often called an acid-base reaction, and it is an acid-base reaction, but it also can be classified as a double replacement because this is our acid, hydrochloric acid, this is our base, sodium hydroxide. When acids and bases react, when we have strong acids, strong bases react, we get water and a salt. And notice it is a double replacement because the hydrogen now is bonded to the hydroxide. So again, this is another scenario where we don't want to think of water as dihydrogen monoxide. We want to think about it as hydrogen hydroxide because that is how it's reacting. The hydrogen comes off, goes to the hydroxide, the sodium to the chlorine, and we have our double replacement. Our last type of chemical reaction here that we're going to look at is combustion reactions. Combustion reactions, pretty easy to identify. Our most common type of combustion reaction is this. If we have a carbon compound, any type of carbon compound, so in this case it's propane, but it could be butane, C4H10, or it could even be a sugar, C6H12O6. Any type of carbon compound that's here will burn in the presence of oxygen to form these two products, primarily these two products if we have complete combustion. Now, if we have incomplete combustion, we could form carbon monoxide or some soot, but in complete combustion, if we have enough oxygen, then we'll form CO2 and water in every type of combustion reaction of a carbon compound. So now there's a list here of some chemical reactions, and I just want to be able to go down the list and see what types of they are, and see if we can predict what the products are going to be. So in ABC, I cut off A. I think it's over here. Notice hydrogen with chlorine. It is there. This is again from your book. These are all synthesis reactions. We have two things coming together to make one. Notice magnesium and oxygen to make magnesium oxide. Now barium oxide and water. If those come together, now what can we form in a synthesis reaction? Well, what we're going to form in a reaction like that, if it's synthesis, is again, we have to start looking at that water as hydrogen hydroxide. And what we will form in this reaction is barium hydroxide, like this. Again, how do you know that right now? You don't really, but we need to start seeing patterns and seeing these types of reactions so we can predict other ones that we'll run into. Notice our group B reactions here, and let me make things bigger so that we can see them and kind of decipher things here. Our group B reactions, these are all decomposition. We have one thing breaking into pieces, one thing breaking into pieces. And again, this is classic for a carbonate to break into CO2 and water, a chlorate to give off its oxygen. Now, if we have water and we run electricity through it, this was an example in your book. We kind of skipped over it, but we can actually break this element into its elemental parts, hydrogen and oxygen. Now, notice again, I wrote those as diatomic because they're part of some of our hexahalogens. So if it breaks it apart into hydrogen and oxygen, I need to make sure it's H2 and O2. One other bit with this, we can run electricity through a lot of compounds, through most of our ionic compounds, and break them into their individual elements. So that is an option. Electrolysis will separate most of our ionic compounds down into their elements. Okay, in our group C reactions, we have calcium going together with water to make a hydroxide. So notice hydroxides are very common compounds. So they're easy things to predict from these reactions. Now, what type of reaction is this? This is a single replacement because, again, let's think of our water as hydrogen hydroxide, and that calcium is coming in and kicking out the hydrogen right here, bonding to the hydroxide. We get hydrogen gas as a product. So this is a single replacement. This also is a single replacement. Notice the bromine is coming in, kicking out iodine because the bromine is more reactive. We get iodine out there. C, also a single replacement. Now we have to predict the products of this. We have to know that zinc is always a +2 metal ion. Chlorine I know is -1, so we'd have ZnCl2. That's supposed to be a L, or Cl, sorry. ZnCl2, and our other product here is hydrogen, but it can't just be H, it has to be H2 because it's diatomic. And then we'd go through and balance it. But that's not what we're doing right now. We're just trying to identify and predict the products if need be. Now notice all of these are double replacement options. Silver and sodium switching spots. So silver is bonded to the chlorine, sodium to the nitrate, and they switch them off. So we take them apart, swap the cations, and those are our products. Next one, iron sulfide and hydrochloric acid. Similar thing, iron with the chlorine. Here we go. Hydrogen with the sulfur, and there's our other product. C here, also a double replacement. This double replacement is a special double replacement because this is a strong acid, sulfuric acid, potassium hydroxide as a base. Our products are water and our salt, potassium with sulfate. Now we have to know that potassium is +1. You can find that on the periodic table. Sulfate is a -2. This 2 right here kind of gives it away that was probably the charge. That's there because our charge on sulfate is -2. So my potassium sulfate would be K2SO4. So notice things are coming together here. Our naming, knowing our polyatomic ions. All of this is stuff that we're going to have to know into the future. It is not something that we can just kind of drop and move on to the next chapter. Last group, combustion reactions. Carbon compounds with oxygen. 2 products, CO2 and water. Carbon, notice this is a carbon compound. It's carbon monoxide, so carbon monoxide can be burnt further. This is a product of incomplete combustion. With oxygen, we make CO2. Propane here, with oxygen, CO2 and water. Thank you. If you have some extra time sitting around reading your book, I would encourage you to go through the section review. Make sure you can identify these types of reactions, synthesis, single replacement, decomposition, and so on. And another fun thing to try to do is see if we can't start predicting some of the products of chemical reactions like we have in this set, and even in this set up here. This is a little bit easier because they tell you what type of chemical reaction it is. Here, you have to know the type and then predict the products.